Let's take a look at how to work our first series parallel circuit. Notice here that we have a 10 volt power supply. We've got a 1000 ohm R1, 1000 ohm R2, 1000 ohm R3, 1000 ohm R4, 1000 ohm R5, and R6 is also 1000 ohms. Now remember, when working a series parallel circuit, we've got to remember all of the rules that apply to a series circuit and all of the rules that apply to a parallel circuit. So the first question I'm going to ask myself is, do I see two resistors in series? In this case, these two resistors are in series. Also, these two resistors are in series, and these two are in series. So when you ask yourself the question, do I see two in series? The answer is yes. You combine them, and then you redraw the circuit. So 1000 plus 1000 would be equal to 2000 ohms. 1000 plus 1000 would be equal to 2000 ohms. And 1000 plus 1000 would be equal to 2000 ohms. Now the key to this is redrawing the circuit. So I combine these, then I'm going to redraw the circuit. So I've got my 10 volt source. Remember, I combined R1 and R2 and got an equivalent resistance of 2000 ohms. Then I combined R3 and R4 and I got an equivalent resistance of 2000 ohms. Then I combined R5 and R6 and got an equivalent resistance of 2000 ohms. So now, if I go back to the same question, do I see two or more resistors in series? The answer in this case is no. So my next question is, do I see two or more resistors in parallel? The answer would be yes. These two are in parallel. So now I'm going to use the parallel formula for resistors, which means 1 divided by 2000 plus 1 divided by 2000 equals, and then I inverse the answer, and I would get 1000 ohms. You can also use the formula if the resistor values are the same exact value, then you simply take that value and divide it by how many there are in parallel of that same value. So 2000 divided by 2 would be 1000. So now we've got to redraw the circuit. So I have my 10 volt source. This was the R1 and R2 that were combined into an equivalent resistance. And then this resistance is representing the equivalent resistance of R3 and R4 and R5 and R6, which we calculated to be 1000 ohms. Now if we go back to that question we were just on, do I see two or more resistors in parallel? The answer is no. So I've got to go back to the other question. Do I see two or more resistors in series? Well, yes, these two resistors are in series. So I would combine them. 1000 plus 2000. So the RT for this circuit should be 3000 ohms. When I get my circuit worked down to one resistor in series, then that's as far as I can go. So RT for this circuit would equal 3K ohms. Now knowing that, I can calculate the total current. And you remember the total current is going to be the source voltage divided by the total resistance. If the source voltage is 10 volts and the total resistance is 3000 ohms, when I perform that calculation, I should come up with 3.33 milliamps. Now what this means is I have a total current of 3.33 milliamps flowing through that equivalent resistance. That means there's 3.3 milliamps flowing through these two resistors. Remember, this is a series circuit, right? And the current in a series circuit remains the same. Now, if I know I've got 3.33 milliamps flowing through this 1000 ohm resistor, how many volts would that give me dropped across this resistance? Well, if you take your 3.33 milliamps and multiply it by 1000 ohms, you should get like 3.33 volts. So this equivalent resistance here is dropping 3.33 volts. This 2000 ohm resistor, if I take 3.33 milliamps times 2000 ohms, the K and the milli would cancel out, so 2 times 3.33 should be 6.67 volts. Now you remember in a series circuit, Kirchoff's voltage law says that the sum of the voltage drops in a series path will equal the source. 6.67 plus 3.33 should come up close to 10 volts. Now we're going to take this circuit and we're going to go back to the previous circuit. Remember, we had these two resistances that we combined into this resistance. This resistance is dropping 3.33 volts. And since these two resistors are in parallel, what do we know about parallel voltage drops? That means this resistor would be dropping 3.3 volts, and this resistor would be dropping 3.3 volts. If I know the voltage drop across a resistance, and I know the resistor value, would that allow me to find the current through that resistance? Absolutely. So if I take 3.33 volts and divide it by 2000 ohms, I'm going to get a current somewhere around 1.67 milliamps. 3.33 volts divided by 2000 should be somewhere around 1.67 milliamps. Now 1.67 milliamps plus 1.67 milliamps, does that add up to 3.33 milliamps? It should be. Remember, this series circuit here, I've got 3.33 milliamps, the total current flowing up through here. So that would mean that the total current flowing back to the source, see right here, the current through this branch, the current through this branch adds up to the total current going back to the source. So I've got voltage drop across this resistance, voltage drop across this resistance, the current through that resistance, the current through that resistance, and the current through that resistance. Now we can back up to our original circuit. And if I know I have 3.33 milliamps of current flowing through these two resistors, then I can simply take 3.33 milliamps times 1000. The milli and the kilo should cancel, so 3.33 times 1, that means R1 should be dropping 3.33 volts. 1000 times 3.33 milli, R2 should be dropping 3.33 volts. Then we had 1.67 milliamps flowing through these two resistors and 1.67 milliamps flowing through these two resistors. So current times resistance equals voltage drop. The milli and the kilo will cancel because that's 10 to the negative third, that's 10 to the positive third. So 1.67 times 1, that means R3 should be dropping 1.67 volts. And R4 should be dropping 1.67 volts. Same thing here, 1.67 milliamps, 1000. R5 would be dropping 1.67 volts, and R6 would be dropping 1.67 volts. Now as far as calculating power dissipations, we've got three formulas. Power equals voltage times current. Power equals current squared times resistance. And power equals voltage squared divided by resistance. So if I'm looking for the power dissipated, and power dissipation means how much electrical energy is converted into heat and light energy in this resistor, I can take the voltage drop across this resistance times the current through this resistance, or I could take the current through this resistance, square it, times that resistance, or I could take the voltage drop across that resistance, square it, and divide it by that resistance. No matter which formula you use, you'll get the same answer for all of those. So I'm going to get my calculator here, and I'm just going to use V times I. So the voltage drop across R1 is 3.33 volts times the current through R1, which is 3.33 milliamps. So I come up with an answer of like 11 milliwatts. I've got the same voltage and the same current on R2, so that would be 11 milliwatts. Now here I've got a 1000 ohm resistor dropping 1.67 volts. There's 1.67 milliamps of current through it. In fact, since all these resistors are the same value, they're all dropping the same voltage, they all have the same current through them, I can do this calculation one time for all 4 resistors. So I'm going to take this current, 1.67 milliamps, times the voltage drop, 1.67 equals, and for the power dissipated in R3, I come up with like 2.78 milliwatts. I've got the same voltage drop and the same current through this resistor, the same voltage drop, the same current through this resistance, and the same voltage drop and the same current through this resistance. So all 4 of these would be dissipating 2.78 milliwatts.